Welcome to more limits and continuity and probably in the second video, the intermediate value theorem. So it says if direct substitution does not give an answer to a limit problem because an indeterminate form is obtained, which he says is usually 0 over 0, but honestly, I don't care about what's on top. What I care about is that division by 0 is bad. And it says let's use algebraic techniques to change the form of the limit. So we do this when we can't look at the graph, right? So if we can't look at the graph, it turns out we have some algebra tricks that we could use. So I wanted to talk about each one of these problems and say, hey, if I plug in a 0 right here, then it doesn't matter what's on the inside because 0 times anything is bad. Now technically what's on the inside is 1, and so 0 times 1 is 0, and that would be bad. And here, if I plug in a 2 and I square it and then I take away 4, that would also be 0, and that would also be bad. And here, 1 minus 1 ends up being 0. 1 minus 1 ends up being 0. And here, this one's a little bit tricky because I'm not going to plug in 2 exactly anyways, so we'll come to it in a moment. So is there anything that we can do to sort of make, still find a limit even though, my immediate path of just plugging in the number didn't work? Well, I'm hoping that when when you're seeing these problems, you're like thinking to yourself, oh yeah, this is x over x. That's pretty simple to me to simplify in such a fashion. And so I will rewrite it in its new simplified form. It will be the limit as x approaches 0 of x plus 1. And you might remember from pre-calculus that we should make note of the fact that there is a hole at that point. And what my y value is, I'll find out in a moment, right? So I'm saying that now that I have factored out those x's, I can plug in a 0 right here, and I can get 1 over 0 plus 1, which is just 1 over 1, which is 1. And I can say for certainty that there is a hole there, but the limit still exists, okay? And the limit would be 1. And it's definitely a removable hole because I factored, and that allowed me to remove that hole. So now we look at number 2, and in the denominator, hey, you might be able to factor that. It's difference of squares. So we could say that this was the same thing as x plus 2 times x minus 2, and the x minus 2's cancel out. So then I would rewrite this as the limit of 1 over x plus 2. And if I check now at a positive 2, I'm still good. I have 1 over 2 plus 2, and that equals 4. Again, there is a hole though, and that hole is at 2 and 1/4. And it was removable, and we removed it, and now we can find the limit. Now, with number 3, please double check the freestyle if you don't remember sum or difference of cubes. You definitely could use long division or synthetic division on this, but I prefer to use my cute mnemonic SOAP, same, opposite, and always positive. And right now, in these days, SOAP is really important, isn't it? So I am even more pleased to introduce it to you in that freestyle. So I will say then that this is x being cubed, and this is 1 being cubed. And remember that the first thing is just the two things that were being cubed, and then the last thing had 3 things in it. It would be something squared, it would be this squared, and then inside it would be those 2 things multiplied together. So this, oh, look, I don't want to put my signs down just yet. It would be those 2 things multiplied together. And remember SOAP, same, so same, opposite, and oh, always positive. And so I factored it. And now on the bottom, I say this is x minus 1. And there was always a hint to you that this could be factorable because, hey, these negative ones match. And so you could have imagined that it would be factorable there. So now I'm going to simplify, and I'm going to say, oops, I forgot my notation. And you'll notice this, I get a little lazy. You guys might get a little lazy too. Please be very careful on the AP exam when you give an answer. If you're trying to say a limit, go ahead and write the limit. That way we don't forget what it is we're doing. And in fact, I will make it even look pretty. I'll say the limit as x squared plus x plus 1. And hey, there's nothing in the denominator except for a 1 now. And that limit is as x approaches 1. Well, that's very easy for me to calculate, right? This is 1 squared plus 1 plus 1, which ends up being 3. And so I can say that that whole is at 1 comma 3. All right, so I did those. And then on number 4, I gave you a topic where I talked about rationalizing the denominator and kind of why we do it. And so I'm hoping that it doesn't hurt your feelings when I break it out, because I extended that idea in the freestyle about why we would maybe factor something that looked pretty and then turn it ugly and then put it back together again. So right here, I can see these two things have a relationship. And you're going to practice with these a bunch, so you'll see. And basically what I'm going to do is called rationalizing the denominator. And if you need more help, you can ask for it. Don't worry. So I am going to multiply by the square root of x plus 1. It is the complex conjugate. So I've given you 2 vocabulary phrases you can look stuff up on the internet with. And when I multiply complex conjugates, I know what ends up happening. And I've shown you this actually in the freestyle, long ways. What happens? I end up with an x minus a 1 on top. And on the bottom, super ugly thing, why did I do this? Well, here's why. You're about to see it, okay? So I'm looking for the limit now as x approaches 1, and 1 is no longer a problem for me because look, these cancel out. Ta-da! Now there's just a 1 on top, and so I'll write this as the limit, and I'm going to put equal signs here and here. And right here, I'm putting multiplication signs like, parentheses around to tell you that I was multiplying by that complex conjugate. And I say this is the limit as x approaches 1. And what about what's on top is still a 1. Please don't forget that even though you cancel stuff out of the top, that there's still stuff in the denominator. And this is the square root of x plus 1, which can easily be evaluated because the square root of 1 is 1, and 1 plus 1 is 2. So 1 plus 1. I now have a value of a half, and I could say that there is a whole here at 1 and 1/2. Okay, and I'm putting boxes around my answer so you can see the actual answer, because technically this question didn't ask you what kind of discontinuity was there. It just asked you about what the limit was. But a lot of kids, for a while you're like, well, what kind of discontinuity is it? So I want to tell you as we're going over it. And again, I mentioned number 5 is a little bit more complicated. I don't see anything that cancels out. And so my technique is to just talk about what happens from the plus side of 2. So I'm going to sort of algebraically estimate what I think is happening. And so a number that's very close to 2, but coming from the right would be a number that's bigger than 2. So I'm going to plug in 2.01, and I'm going to say I have 2.01 minus 2. And what do I end up with? Well, what I end up with is 2.01 divided by 0.01. And what you might recall in the freestyle I showed you, I literally showed you this problem, is where we multiply and we end up with a large number. And that large number tells me that I can approximate this limit to be positive infinity. And don't forget that there's that controversy in the math world which says, well, when in doubt, you can also say that it does not exist, because we argue about whether or not things can approach infinity from the left and from the right, because they don't actually technically ever meet. So when in doubt, go ahead and guess does not exist on a multiple choice question. All right, so then we have 2 very lovely problems. These are very, very strong AP style questions where it says, please discuss the continuity of this piecewise function. Well, from factoring it, I would get x minus 3 times x plus 1. And as I'm factoring it, I say, oh, okay then. So this just simplifies to x plus 1. And I say to myself, well, what is happening with the graph? Like, where is the piecewiseness of the graph? So let me just, draw a quick example of it for you, where I say that I'm starting at 1 and I'm going up 1 over 1 a bunch of times, and there was that hole at x equals 3. So if this is 1 and that's 2, that's 3. This is 1, that's 2, that's 3. There's a hole right here. And that height is 4. Yeah, 4. And so I can say then that if it's telling me right here that that's a height of 5, that would be bad. I mean, bad for continuity, right? I'm going to go ahead and say then that there is a hole at the value that I get here when x is 3 is I get a 3 plus 1, which is a 4. So when x is 3, I get a 4. All right. And the point is defined at 5. So I could call this a removable discontinuity as long as I get rid of that piece. Like literally, just cross that. Okay. Now for number 7, I say if g of x is this crazy looking thing, and I don't know about you, but I already have enough variables in my life. I don't need any more. I'm upset now. So if it is a continuous function, though, I would want to find the value of a. And I'll mention that I'd like to go over this problem in class and show you what we can do with sliders and Desmos. But technically, I'm hoping that it's obvious that whatever I get when I have x equaling 2, I want to get the same thing on the other function. That way, if I have two pieces of a Desmos graph, just any graph, if I have two pieces of a piecewise graph, I want them to come together. And so is it obvious then that I'm going to do this? 3x squared plus a equals x minus 3. And I said I wanted to know what happens when x is 2. So is it obvious now that I'm going to do this? 3x is now a 2 plus a, and x is now a 2. And then I will end up with, ready, 4 times 3 is 12 plus a equals negative 1 minus 12 from both sides, and I find out that a equals negative 13. Oh, clever. We do a lot of, putting two things equal to each other in calculus. I'm hoping that we make that connection in your brain, that one thing equals another. When in doubt, set them equal to each other and see what happens. Hey, so I've typed in our equations, and I didn't hit enter yet because I just wanted to show you how lazy I am. I know that there's a fraction button on the calculator, and I just wanted you to know I always forget to use it. I just like to put parentheses around the top and parentheses around the bottom and the division symbol in between. That way, when I hit enter, boom, I'm done. Another thing I wanted to mention was control and that key. Again, please watch my keys light up for you. Control and that key will give the colon equals, which allows you to define a function. Another thing I'll say is that I know that there's a table in the TI Inspire, but I really find it simpler to go ahead and start typing in the numbers that I was interested in by hand, because the settings kind of escape me in a high pressure situation like the AP exam. So I'm just going to throw all these numbers in here, and then, hey, one other thing, please watch me. Hold on a minute. I want you to know I love this feature of this calculator where you are able to, ready, scroll up. So watch the red keys, see what key it is that I'm hitting to go up. Boom, it's the up key. Hit enter, and now I can edit that line. And so I am slowly but surely gathering all of the values that we need for this calculator example. Ta-da! And now we can throw them into our table on our lecture notes. If you've been with me for a while, then you know how supremely lazy I am. And by the way, also look, Mr. Taylor has amazing, impeccable handwriting. So I've just snagged this from his answer key. So now let's talk about what we think is happening with the limit of this thing. And I notice that here, as I'm approaching from the left, I feel like I'm getting very close to positive infinity. And as I'm approaching from the right, I feel like I'm getting close to negative infinity. So here he says does not exist. And I totally agree. With the next one, I think it's not quite as obvious because it's like, well, I'm getting close to something, but I don't really know what it is. I'm getting close to something, but I don't really know what it is. And right here, though, ooh, that thing, I know what that is. That's 1/3. As a repeating decimal goes on for forever. We should be able to recognize that. And look, here I didn't know, here I didn't recognize, but that, ooh, is super close. So I'm going to go ahead and say then that I believe that the limit would be 1/3. And he says, and this is a trick question, can a table like these tables be used to find limits with absolute certainty? And the answer is no. And it's a trick question because you do have the function, okay? So I know what f of x is. I think what we're talking about here was if I just gave you the table without the function, and so you know stuff about rational functions. You've been taught a lot about it in pre-calculus. We've even been talking about it here in calculus. And we believe these things to be continuous except for where they're problematic, where they're asymptotes, which it looks like the denominator is pretty complicated. It might take me a while to find all of those roots. I'd be using the fundamental theorem of algebra. So I think if we just looked at the tables without knowing any of that other information, that's where you can't say for sure. And put yourself in the shoes of, the ancient calculus gods, Newton. I haven't maybe mentioned their names in class, Leibniz. These guys, they decided that they could say things for certainty, even for values that they had not yet calculated, because they use algebraic techniques and, the strength of actual theorems to help them accomplish their goals. So if we just look at tables, we can't say for sure what's going on because between these two numbers is actually an infinity of more numbers. It's not just an infinity, it's an infinity to the infinity of numbers. Okay, because like I have 1.999, and that add an extra 9 is still less than 2.001. And even there, between 1.999, there's another number, and it's 1.9999. And there's still even another number in between there, which is 2.0001. That class, by the way, when you go to college, is called real analysis. And I swear I've never had a better time. It was so fun. It was great. I really highly recommend that class, real analysis, the concept of an infinity to an infinity. Pair that semester up with astronomy, and you are just going to have a great semester. I promise you. Okay, so now that I've done my version of the intermediate value theorem in this freestyle, we have this if f is continuous on the interval a to b and k is any y value between f of a and f of b, then there is at least one x value, which we could call c, that is going to be between a and b, such that the height at that input is going to equal a certain number. And so I say this is a height at that input that equals this certain number. And so the wording of it's very strongly, there's so many, so many variables in this wording of this theorem. But we've talked about it, and hopefully you're feeling comfortable with the idea of it. So number 9 says, does the intermediate value theorem guarantee a C value on the given interval? And so we want to check, ready? We want to check to see if it's continuous. And we're going to call that part 1. And then we want to say that k is any y value between these two, and we're going to call that step 2. And then here we are checking to see whether or not that is true. We're calling that step 3. And if we can get through these 3 steps, then we could probably figure out the answer to the question. So number 1, this is a parabola. It's pretty well behaved. I feel fairly certain, and it's quite easy for me to say, that this is continuous. Whoa. Is continuous. Okay, and it is continuous on this interval from 0 to 5. It's continuous everywhere, but definitely it is continuous on this interval from 0 to 5. And I'm going to check right now and say that f of 0, it would be 0, because I plug in 0, so I'm going to get 0, and that f of 5 is going to be 5 squared is 25, minus 5 is going to end up being 20. And then right here, I will say that my intermediate value theorem, and yes, you are allowed to abbreviate this on the test, it guarantees AC value in my interval from 0 to 5 such that f of c equals 12. Remember, that was given to me in the question. So there you go. And I will say that I really wish I could have written all that smaller. So let's see if I can just shrink it down a little bit. There you go. And I might even move this over. Okay, so the next part is where I have been given g of x, and I'm looking at something that I know is quite easily factorable, and I'm feeling pretty good about simplifying that equation if I needed to. But let's see. I think that before I factor, I should recall that there is a hole at 2, which is definitely inside of this interval. So part 1, I will say it is not continuous from 0 to 3. Now, it is a removable discontinuity, but you have to remember that, just because we removed it to find a limit of it doesn't mean that it's in the domain. It's still not in the domain. So I'm saying that it's not continuous, and therefore the IVT does not apply. Okay, and that means that there's no more steps to this problem. If you find out that the intermediate value theorem cannot work, well, there you go. So number 10 says find the value of c in example 9a, and I'm wondering, what do you think I'm going to do with that x squared minus x, oh, sorry, I just said it out loud, and that 12? Obviously, I already mentioned, when in doubt, set things equal to each other. Ready? X squared minus x equals 12. And I'm going to minus 12 from both sides. And I now have x squared minus x minus 12, and that equals 0. And I factor it. I get x minus 4, and I get x plus 3, and that equals 0. And so my answers are x equals 4 and x equals negative 3. Guess what is not in my interval? Remember, my interval was from 0 to 3, so negative 3 would not be in that. Therefore, this is my c value. And you're like, you haven't used c anywhere else. That's okay. If you just call it x on the AP exam, they don't mind either. You're certainly welcome to use c's. I could have said c squared minus c minus 12. Right here, I could have turned, just from the beginning, I could have said c, I could have said c, but I just find that that's an extra level of confusion that nobody needs. And so if you say x equals 4 on the AP exam, they totally grade it correctly. And this is in the interval from 0 to 5. And some students at this point might say to me, do I have to write that, in the interval? Do I have to write over here number 1 and number 2 and number 3? Yeah, it turns out words are how you answer these. And so please do be careful when you do your work. If it's asking you about whether or not the interval sorry, whether or not the intermediate value theorem can be used, you have to go through step 1, step 2, and step 3, and you do have to write words in order to say that you've thought out that process, okay?